we're going to do is section 6.1, we're kind of going backwards. We're going to look at length of arc, or arc length. So section 6.1, arc length. Length of arc is what the book calls it. Others call it arc length, so I'm going to call it arc length. Prime is also continuous, so the derivative is continuous on the closed interval. So let's just kind of look. We have a curve, and it looks like this from A to B, okay? And if it's a, if it's a polynomial and the derivative is also a polynomial, it's going to be continuous. It's not going to be a problem, right? So smooth, no sharp turns, stops, jumps, rips, tears, sharp points, any of that. Then if we have two different points on here, so I'm going to do my version of this. You have the book version that you can also look at. So I'm going to call it x sub 1 and x sub 2. We got 2 points, and if I look at those points on the graph, that'd be right here and right here, right? So this would be f of x2, this would be f of x1, and if I draw a line that connects those dots, that would be close, right there. So basically the red line connecting those dots is an approximate, so let me blow it up over here. Here's the curve. Anyway, this straight line that connects those dots is an approximate length. Does everybody agree? So what we're going to do is we're going to let L denote the length of the graph. I don't want to mute. Let L, so I'm going to use capital L, denote the length of the graph. So that'd be the blue. That blue piece. So that's longer than the red one, right? In the way I got it drawn. The blue, a closed interval A to with basically x sub 0, which would be A, right? So this is A, x1, x2, etc. All the way through x sub n, which would be the letter B, right? Or the number B, not letter B. Number B? That doesn't make any sense. But anyway, so anyway, what we're going to do is we're going to split this up, and if I want to measure that, basically the length of the portion of the graph between those. So this is like delta L sub k. So the change in change in that, and what we can do is we can just look at this as we can approximate it with delta y over delta x, right? Would be this. Well, no, that's the slope. But this is a change in y. That's change in x. But if I want that length, so if I have red L be the length, what would it be? The red length, so this change in the length, I'll call it delta L, is going to be the square root of delta x squared plus delta y squared. Everybody agree? Right? Pythagorean theorem. Length of that side, if I called that C, would be a squared plus b squared equals c squared. So it's the square root of that. But anyway, delta y, what's that? That's going to be the delta y over here is f of x sub 2 minus f of x sub 1, and delta x right here is going to be x sub 2 minus x sub 1. And so anyway, so the length of the line segment, actually I'm going to cut. I don't want that one to be L sub k. I want this one, delta L sub k. So that's the kth interval. They might call it the nth interval in the book. But anyway, if I want that length, delta L sub k, what would that equal? That would be the square root of x sub, well, in this case, it's x sub 2 minus x sub 1. But in general, if this is, now I'm going to change this x sub k minus 1 to x sub k. So it'd be x sub k is bigger minus x sub k minus 1. Quantity squared plus the top, this would be, the top one would be x sub k. This would be x sub k minus 1. So it'd be plus f of x sub k minus f of x sub k minus 1. Anyway, long story short, quantity squared, right? And it's the square root of that whole thing. So let me clear this. I know you were writing that down, but you can go back and look. Anyway, long story short, it's not really Riemann sum. So what we're going to do is we're going to take the limit as the norm of the partition goes to 0. So if you remember Riemann sums back in Calc 1, kind of glazed over that when we had equal ones. We just called it, you know, delta x, right? B minus a over n and let n go to infinity. Those were all the same size. If they're different sizes, we called it the norm of the partition. Long story short, I'm going to leave the proof out of it, but that's going to imply with some proof and results in the book, which I'm not going to go into the detail on this. I'm just going to give you that that length, arc length of the curve is going to be the sum I equals 1 to n of the delta L sub k's, and this is the limit as the norm n goes to infinity, right? So, or the norm, or the limit as the norm of the partition goes to 0. Either way, we can do it either way. But anyway, what's this going to equal? Let me just, it's going to equal, you know, if we're looking, so it's the limit, and then we've got that sum of these square root. What ends up happening there, what do you know about the slope of the tangent line? It's the derivative, right? Okay, but anyway, so it's going to be the sum of, well, I'm not developing this. Let me just, whoops. Basically, what it ends up being is the definite integral from a to b. So we get a nice result because of slope of the tangent line and all that. But it's 1 minus f prime at x quantity squared, and then dx. Okay. So basically, there's a mean value theorem that we can use to help prove this, which I didn't really, it's been a long time since we've had that. You can read through that, but long story short, we end up with a very nice result here. Okay. So I wanted to give that. That's one of the things that also comes up in chapter 9. That's why I wanted to give it to you. If we have, this is where y equals f of x, right? So kind of normal way to write it. But what if we have it, what if we have x equals g of y? So if we have a vertical representation or flip the x's into y's, we can still have, we can integrate instead of from a to b, we can go up from c to d. So then this length would be the definite integral from c to d of the square root of, sorry, this is wrong, go back. It's not 1 minus, it's 1 plus. It's 1 plus. So this is 1 plus g prime at y, quantity squared, dy. So if you wanted to integrate above, we could do that. Okay, so let's look at how much time I got. I want to at least get through this section and give you 5, 10. Yeah, okay. Well, is there an odd? So instead of you doing the odds, why don't we do an odd? Because you got the example in the book just like I did. That's lines. I want a curve. Okay, let's do number 5, shall we? This is page 540. You still hear me?
Yep.
Perfect. Okay. Find the length of the arc of the curve. We've got 9y squared equals 4x cubed. From the origin. So we want to find L from the arc length from the origin, which is 0, 0 to 3, and then 2 root 3. So let's draw a picture of this first. I need to solve that in terms of y, right? So what's f of x equal? Right? So we got y squared equals 4 9 x cubed. And then, which implies y equals the square root of 4x cubed over 9, which we can take the square root of 4 as 2. So this is 2/3 x to the 3/2, right? Now, for, as far as absolute value and all that crap, do we need to worry about it? No, because x is greater than what? Greater than or equal to 0, right? On this, when I'm going from here to here. Okay. So anyway, if we wanted to, so of course this y, this is f of x, right? So f of x equals this. First of all, is that continuous? Yeah, where do we have a problem? Well, square root of a negative number, correct? Because this is the square root of x quantity cubed, right? Or x cubed and then square root. So if x is negative, it's a problem. But for positive x's and x equals 0, we have no problem, right? So we can take the derivative. So if it's differentiable, is it continuous?
Yes.
Differentiability is stronger, so differentiability implies continuity. So we could take f prime exists, right? That implies that f is continuous for on including 0 to 3. So I'm looking for the x values are from 0 to 3, right? So f is continuous. What else do we need to have be continuous? F prime. Didn't I say f prime has to be continuous? So what is f prime? Let's just calculate f prime. F prime, where you can use the power rule. So it's 3/2 times 2/3 is 1 times x to the 3/2 minus 1 is x to the 1/2, which is the square root of x. And what do you know about that? This is continuous on 0 to 3 as well. It's in fact 0 to not including infinity, right? And of course, at 0, we gotta remember. Do you remember in chapter 3, I made you show right-handed continuity at 0? Do you remember all that? And it was like kind of a pain in the butt for continuity on a half open interval or a closed interval. Okay. So anyway, so we know right away it's 0 to infinity is fine, but I could show right-handed continuity at x equals 0, so then we can include the 0 there. Anyway, so it's a continuous function, continuous on its domain, square root of x, right? But that's what f prime at x is. So basically, we've satisfied the hypotheses of the theorem, right? So what did it say? Let f and f prime be continuous on the closed interval. They are. So the hypotheses are satisfied. Now let's go ahead and calculate. Let's go ahead and calculate the arc length. So the arc length is going to be the definite integral from what to what? For this one. Starting at the origin and going to x equals what? 3 of the square root of 1 plus f prime at x. What was f prime at x in this case? Square root of x, quantity squared, right? And then dx. So what's this equal? Definite integral from 0 to 3 of the square root of 1 plus x dx. Oh my. What are we going to do here? Do you remember? I don't know how to. So we're going to let u equal 1 plus x. So what's du? du is dx, right? So this is going to be equivalent to the square root, definite integral of I don't know to I don't know of the square root of u, which is u to the 1/2 du. Everybody agree? Which is u to the 3/2 over 3/2, so times 2/3, evaluated from I don't know to I don't know. So I'm going to back sub bs, if you remember back sub, and I'm going to go to the right and put it in blue again. So with the back substitution, bs, I'm going to go to the left, sorry. I'm going to go across the screen. Anyway, over here, what's that? That becomes 2/3 the x plus 1 to the 3/2 power, right? 1 plus x is the same as x plus 1, right? Maybe I should put in 1 plus x, but it doesn't really matter. Evaluated from 0 to 3, right? So what's this equal? Well, if I plug in the 3, I get 4 to the 3/2 power. Well, it's easier to take the square root first and then cube it, isn't it? Square root of 4 is 2, cubed is 8. 2/3 of 8 is what? 16/3. Minus, and then if I plug in the 0, I get something. So it doesn't go to 0. It's 1 to the 3/2 power. 1 to any power bigger than or equal to 0 is 1, right? So it's minus 2/3. What does that equal? That equals 14/3 units. Now, if this is in meters or centimeters or inches, right, we would label it that way. But it's 14/3 units. And once again, if I'm drawing a graph of that and it looks like this, some arc length from 0 to 3, that is the length. So I'll give you a couple odds, a few odds to work on, just to make sure you get the concept down. The toughest part of this is coming up with the formula that utilizes the mean value theorem. So I'll just let you read through that. That's not something that you have to reproduce. But know the formula for arc length. And the f prime and the 1 plus f prime quantity squared shows up because we can factor out a delta x, which becomes a dx when everything gets tiny. Sound good?
Sounds
Okay,
good.